All right, stats. Today we're going to talk about two sampling stuff. We're going to start with proportions. And so it's going to work very, very similar. First thing is to realize that when we're doing two proportion problems, we need to make sure that the two proportions are from two different groups. And it's okay for them to be two different size groups. It also is okay for them to be experiment groups as long as the treatments are two different treatments. Okay, so two sample means that they are taking a sample from one pond and another sample from a completely different pond and then comparing them together. Okay, so all of the conditions are still the same. We're still checking for random, for independence, for normality. Now we just have more to work with. We have to check each individual proportion and make sure each one is at least 10. And since it's a two sample now, we'll continue even if it's at least 5. So they say the rule is at least 10, but 5 is fine too. And for the 10% rule, we've got to check each individual sample as well. Okay, so and for the randomness, you got to check both samples. All right, so for our interval, we usually start out with what we think our guess is. Well, we can't guess at 2 and put them into one equation unless we do a difference between the groups. So that's going to be the key thing now, is we're going to do a difference between the groups. So when you do a confidence interval, it's now going to be the two proportions subtracted from each other. In either order, it does not matter as long as you tell them in the setup that that's the way you're doing it. The other thing that's going to change is the formula for standard deviation. Notice we're still doing the z because it's proportions. And now the standard deviation is going to be the first proportion times 1 minus the first proportion over the first group, and then a plus sign, and then these, right? Because we always add together when we're doing standard deviation. So we're just finding the standard deviation of each proportion within its sample separately, and then adding them together underneath the square root. Under our calculator, we're going to be doing 2 prop z interval, okay? And make sure that you are doing a prop, not just a 2 sample z. A 2 sample z would be a means problem, one of those rare cases, okay? All right, so if we do a test instead of an interval, okay, so the first part was all about intervals. Where can I say that? So this is all about intervals. So confidence intervals, okay? And the second thing we're going to talk about, because they're so similar, we may as well do them at the same time, is significance tests with 2 proportions. Okay, we're going to check each group again individually. Random, we're going to do the same thing, 2 different random samples from 2 different populations or 2 different treatment groups. We're still going to check each individual sample and population. We are going to make sure they're randomly selected or randomly assigned in an experiment. We're going to do the large count rule. So we've taken care of all those. So in the large count rule, again, we're going to say at least 5 is okay, but we're going to check to make sure. Hopefully they're at least 10, but at least 5 will still keep going. All right, on this one, we're going to need one extra piece. And again, your calculator will take care of this for you, but you need to know what's going into your calculator. So anytime we're doing a 2 sample proportion test, and that is the key idea here, okay, we are going to pool our proportions. So one of the things I always remind each other is in a test, you always pool proportions, not means. See how they both kind of rhyme? They both start with B. Pool proportions, not means. Okay, so for our test on this one, we're going to do something to move for the standard deviation. We're going to move all of those proportions together for a test. And to do that, they're going to call it P hat sub C for combined. So combined is just going to be your total numerators for each one of the proportions added together, and then over your total sample sizes, your denominators added together. Okay, now where are we going to use that? It only gets used when we're figuring out standard deviation. Our hypothesis test is going to be P1 equals P2. Remember, these are population things. Okay, so P1 equals P2, or you could also call it P1 minus P2 so that it matches more, looks more like our confidence interval stuff, if that makes you feel more comfortable. You could subtract them and say then the null hypothesis is 0. The alternative could be anything. So the alternative could be P1 is greater than P2. If that's the case, imagine that you moved the second one on the right-hand side over to the left side. If I did that, I would be doing P1 minus P2, same way that they did over here, and then I would say greater than 0, right? So same thing, very similar. If it's less than, it's going to be minus is less than 0, and if it's a not equals, it's going to be the minus is not equal to 0. All right, our new z-score is going to be the difference of the two proportions. And then this is your HO, right? It should be 0 because we're already comparing the two proportions. There's nothing left. There's no other numbers. Okay, and then the formula is going to be that combined proportion, what's left of the combined proportion minus 1. And then we see that same thing going on in the denominator where we're going to make sure we add together the two groups. Okay, so this is, again, standard error, even though it's a test, because we don't have really a null hypothesis to go with here for both of our individual proportions. So notice everything, just about, everything from, let's see, what step would that have been? It would have been from A down to make a decision. What's right before make a decision? Oh, obtain a p-value. With the exception of the name, right, is going to be p hat stuff instead of p. Okay, so when we do our initial steps, our p and our h, right, we're talking about what the population looks like, and then we start talking about our samples for a really long time. All right, so what do we do at the end of those? All right, so then we're going to just say either we do or we do not have convincing evidence that the difference between the two true proportions of those two groups, and you again repeat what those two groups are, is different, or this is different. So it's either we have or we do not have convincing evidence. So again, you're going to see a lot of things that look exactly the same as what we were doing before for one proportion stuff. Okay, so let's go through this. I'm going to pause the video a little bit to make it a little bit shorter on the stuff that we're really used to, and then just have it already on the screen for you. Okay. All right, so here we go. Our first step of phantoms, we're still using phantoms, is we now have two population proportions to talk about. So the first one was our first group of teens from 1988 to 1994. And again, I'm just saying the true proportion that had hearing loss. And then I'm going to have to tell them what my p hat is from that sampling. So I may as well put them nearby here. And so I called it p hat sub 1 is 0.15. That's coming directly from the work product itself. Now, I don't know how many out of 3,000 that was. I would have to calculate that. All right. And then the same thing with p hat sub 2. They are saying that that is 19.5. So again, if that was over 1,800, I do not know how many that is. Cool. All right. Let's go and do H, hypothesis. Right, here's our hypothesis test. So our first one is that we're just saying the two proportions are equal. That's going to be our set standard, that they're equal. And then again, I move them over to the same side so that we can see the difference of them. Now this question asked, has it increased? So the null hypothesis is going to be equal to 0. The alternative would be that the second proportion is bigger than the first proportion. So that's why we have our less than symbol here. And again, when I move p sub 2 over to the left side, it's going to stay less than, and it's going to get replaced by a 0. All right, let's go do the assumptions. All right, so here's all the assumptions written out. So for random, I'm saying both groups are randomly selected. For the 10% group, I have to check both populations. So the first one has the 3,000, the next one has the 1,800. And then at the end, I said it's reasonable to assume that there are more than the stated population counts in the 1988, 1994, and the 2005 to 2006 populations. And then for normal, I have to check the size and the proportion is more than 10. In the first group, that's a 3,000 with the 15%. And then I've got to check them again for the 1 minus p. So that's the 3,000 again with 1 minus 15. And then I got to check it again for the second group and the second proportion, and then the second group and 1 minus the proportion. And again, if these were only more than 5, we would still continue. They're all more than 5 or more than 10, so it works. So next we're on to name. All right, also on to the name. This is a 2 sample now. It's a proportion, population proportion. It's a z-test. And again, since they didn't tell us the alpha, it would be at 0.05. So next is on to the test statistic. So z equals. All right, so here is test statistic. So we're following the formula that I wrote down, the P1 minus P2 minus 0 over the square root of all that stuff. So the top part is not that difficult. I just take my two proportions, subtract them in parentheses, do minus 0. The bottom part, I need the combined proportion. So to do that, I had to go over to here and calculate it. So the biggest thing about calculating it is that I have to find out what the two counts were out of 3,000 and 1,800. So remember when I did that normal check where I had to multiply 3,000 by 15%? Well, that would have been my number on the top of the first one and the top of the second one. So I went and put those in, and that gave me those two numbers on the top. And then the bottom were the totals, and I calculate that. So that goes into the standard deviation formula, and then 1 minus is the next one. And then the parentheses 1 over 3,000 plus 1 over 1,800. Now at this point, I'm putting it into my calculator to get the z-score, and I'll do a separate video for how to put these into the calculator. But again, if you just follow the name of it, you should be fine. Okay, so I've got my z statistics. So the next step is the probability statement. All right, so for O of phantoms, I drew my normal curve. I said that this is a normal distribution. I labeled that the z0 is the middle, where -4 is, colored into the left-hand side, which again should match your alternative hypothesis. So then I wrote my probability statement for what I see in the picture. What is the probability that z is less than -4? I say I use norm CDF, but I really used my calculator to give me this value that it was something to the -5th power, which makes it a 0 essentially. Okay, and then we're going to move on to make a decision. So make a decision looks just like our usual one. Compare the p-value to the alpha level. So since 0 is less than 0.05, we reject the null hypothesis. Summary is going to work very similar as well. Summary statement, let me see if I can make this smaller so we can get the whole thing into one screen. So we do have convincing evidence that, and then notice I highlighted up at the top in brown, that the true proportion of all teens with hearing loss has increased between the 2-year ranges between the two groups. And that's it, pretty simple. Let's go and do a confidence interval next. All right, so remember for confidence interval that we're going to follow the letters for panic. So the nice thing is the parameter has not changed between the two groups, nor has the assumptions and conditions. So I get to say that I already stated those and check those above. So we go straight to N of panic, which is a 2-sample population proportion Z interval at 95% confidence interval. All right, so the next thing I still have to do is I and then C. Right, so here's the interval. I wrote down the formula first. Notice all these P's are halves. We don't know the true population, so we're guessing to try to give them a good estimate. So then I put all of the numbers in. Notice that the standard deviation is different than what it was for a test. In the test, we use the combined. Here we don't. We use each one separately. And then that leads us to a confidence interval from -0.067 to -0.0227. Remember that you did have to go and find a z-star score. And so in order to do that, keep in mind that you should be drawing some kind of inverse norm stuff happening here. Get that 1.60. Okay, and then the last thing is our conclusion. And then here's our last one, our conclusion. So again, we start out, we are 95% confident that the interval, we give them the interval, captures the true, and then I went to the problem again and I underlined it in green here of what I'm going to write, so that the true difference between the proportion of all teens in the two time frames is, that it captures the true difference between the proportion of teens and all teens that had hearing loss. Now I want to point out something, even though that these two are both related to the same problem. Notice that if we were doing a significance test and they were equal, we would have expected that their difference to be 0. Look at how close we were in our interval to a 0, to a positive 0. This is how close we were. So we were actually just about 2% away from us saying that we would have failed to reject. So we're incredibly close, and we can see that with the confidence interval. In the next one, we'll do the same write-up with an experiment.